Hi there, my name is Robert Harris. I'm a computer science and data science major with a minor in mathematics here at Carroll College. And today I'm going to be presenting brain training, a slightly nerdy investigation into neural networks. So a quick overview of this presentation. Throughout it, I have a handful of things I'd like to do. I'd like to define what neural networks are, and then go through a handful of examples of neural networks that I've made for this project, being regression through neural networks, classification through neural networks, a convolutional neural network, and some sort of a cool task at the end. So let's start with the first question, which is what is a neural network? In essence, a neural network is a machine learning tool that is modeled after the idea of what the human brain is structured like. The human brain is a series of neurons that once enough electricity has been given, they will fire and communicate with each other. This series of firing allows us to do different processes within our brain. So for a neural network, it is a bunch of layers of nodes with different activation functions. Rather than being a binary, it fired or it didn't, neural networks opt for that they're always firing, but with various degrees of strength to different nodes. On the right example, the input layer is the data that we're feeding in. The hidden layer is where those activation functions would lie. And then the output layer is our final end goal. In this case, it would be a regression, looking for one singular output. The width of each of those lines is also the kind of intensity or strength that each of those nodes are communicating with those thinner lines denoting that they're not communicating as much, and the thicker lines, denoting some sort of meaning or importance. Most neural networks, especially the ones that I'm going to be covering in this presentation today, are feed-forward, and they use backpropagation in order to train themselves. What this means is after it's gone through the first time with a handful of random weights attached to each of those connections, it will go back through, determine what was important, increase those, and then whatever wasn't important, it'll decrease those. Doing this a handful of times gets us a neural network with a bunch of different neurons that more or less scale with how important the data is before predicting our final output. For the purposes of this presentation, I've also added at the bottom the notation I'll be using, with nodes outside of parentheses being the count of nodes or what's going on within each of those layers, and then the activation functions being within parentheses. So the first thing I looked at was regression through neural networks. And what I wanted to do was I wanted to predict user movie scores. Now, if you go on IMDb, you'll be able to see a scale of 1 to 10 of how users rate specific movies. I found a database that pulled about 9,000 plus movies, and I wanted to predict that score. What I ended up doing was I cleaned the data slightly, split it into my testing and training splits, and then I ran two different models on it. The first one being a base linear regression, and the second one being a neural network. With my linear regression, I was able to get a training R squared of 0.216, which wasn't too great considering we usually want that to be a larger number. And I got a testing R squared of negative 4.03 times 10 to the 26th. When you see something like that, you know that something isn't right within your linear regression, and that linear regression really isn't the solution to this problem. After I did that, I created a neural network. After tweaking around the layers, I ended up with the structure seen to the left. The 68 is the input, with the 1 at the end being the output of that singular value. Everything in between is a bunch of ReLU activation functions. What a ReLU function is it's a function whose value is y equals 0 up until x equals 0, and then it becomes y equals x. This is better than using the sigmoid function, which was also popular in neural networks, as we found that through a bunch of training of these neural networks, ReLU functions kind of stood up a little bit better than sigmoid curves. With this model, I was able to get a training RMSE of 0.9703. Again, we want that value to actually be significantly smaller, but in the case of user movie scores, we're saying we can predict within about 1 point of accuracy, which is fairly good. The testing RMSE then was also 1.019, again being right around that 1 point distance. The next question I tackled was classification through neural networks, and I decided to predict a music genre using Spotify data. Again, I pulled a data set from Kaggle, and that contained a bunch of different songs off Spotify, as well as their features, which we'll get to towards the end of this presentation. With these features, I tried to predict one of 10 music genres for it that was predestined by Spotify. Again, I did two different models on this, a K-neighbors and the neural network. The K-neighbors model was able to get a training accuracy of 48.7% and a testing accuracy of 44.8 right out of the box without tweaking any parameters. On that top confusion matrix, you can see the results of it on the testing data. Again, what we want with these confusion matrices is we want a stronger colored diagonal line and kind of weaker curves on the outside. Again, the strength of those colors indicate how many points we're able to accurately predict. And you can see that the K-Neighbors model did fairly well on genre 8, which is classical. On genres 5 and 9, it did confuse them quite a bit, ending up with a fairly even spread across those 4 boxes. Those 2 genres ended up being hip hop and R&B, which the K-Neighbors classification wasn't quite able to distinguish between. Finally, I made a neural network for this problem. Again, after tweaking with the layers for a little bit, I ended out upon my final diagram as seen below. We have 25 inputs going into a series of different neuron layers, each growing in size, and then reducing down to 10 at the end to predict those genres. Again, all the functions in between have ReLU activations, with that 10 having a softmax activation. What that allows me to do is it creates 10 neurons that will more or less all say 0 or 1, and it'll allow me to determine which genre it thinks that this song is most likely to be within. On the training data, I was able to get an accuracy of about 64.52%, and on the testing data, I got an accuracy of 55.17%. Again, although this isn't phenomenal across a 10 classification question, it is fairly reasonable to expect that from a neural network. And with the data that Spotify was giving, it was kind of difficult to predict much more than that, as we didn't know the actual songs themselves. We just knew a handful of characteristic features. In the bottom right, we can see the classification matrix for that neural net. Again, it was able to accurately predict classical music, and then it was also accurately able to predict genre 1, ending up as jazz music, which is kind of strange. Again, it did get confused on the hip hop and R&B labels 5 and 9, as much as the K-Neighbors classification did. But as a whole, it did improve across the middle. The next neural network I decided to look at was a convolutional neural network. And I wanted to predict Pokemon types using grayscale images of Pokemon. Convolutional neural networks take an image and then they break it into smaller pixel grid pieces. They do convolutional work on them and then feed them into a max pooling layer, which shrinks the image down. Doing this a bunch of times gets us a smaller image in which all of the characteristic features of said image are present, or at least, attempting to be represented. The process for this was to import images, make them grayscale, convert string types into a dictionary so that I could actually predict those classes, getting a list of image paths and their respective Pokemon types, and then plugging it into a convolutional neural network. There's no alternative model for this, as image classification is rather difficult to do without a neural network. So for the purposes of this question, I only looked at the neural network itself. As you can see, the structure is somewhat seen below. We feed in 120 pixel by 120 pixel images of Pokemon into a 50 neuron layer of convolutions, doing 5 by 5 areas, followed by a max pooling layer of 4 by 4 pixel areas. We then do that again with 100 neurons and another max pooling. And then we feed it into a flattened layer, which takes the image and flattens it into a single array of values. And then we use a dropout layer to remove any redundant pieces of data within that array. And then we feed it into an 18 class softmax function, which I've already discussed. But what that does is it predicts one of the 18 different Pokemon types for each Pokemon. Some Pokemon can have 2 types. For the purposes of this question, I only looked at their primary type, as that is most commonly associated with their characteristics and kind of main attack sets. Within this, we ended up with a training accuracy of 96.45% and testing accuracy of 92.31%. I felt as though it was important to do grayscale images because, as you'll see on a handful of these Pokemon, oftentimes the color of the Pokemon correlates to what type it is, with more bluish Pokemon being water-based, tan Pokemon being normal-based, green Pokemon being plant-based, and orange ones being ground-based. The difficulties using my convolutional neural network included trying to get the image pathing to work properly, as going through Google Drive and Google Colab was a little bit of a hassle. I also had issues translating the images into grayscale, as I was using 2 brand new Python packages that I hadn't used before. I also had issues getting the neural network structure to avoid overfitting within the data, as well as with the testing and training split, forcing me to manually make a testing and training set of data for this problem. So finally, we have the cool personal task, and this is the one that I was the most excited about. The question I decided to look into was, can I make a neural network that is incredibly simple and can predict whether or not I like a given song? I have a fairly broad taste in music, so I felt as though this would be a rather difficult problem to evaluate in any means other than a neural network. On the bottom left, we can see a handful of those Spotify features that I was mentioning before. When you go through the Spotify web API, you're able to get information about each track, including the danceability, acousticness, valence, speechness, and energy of the track, as well as a handful of others. These are somewhat arbitrary values that Spotify has used a handful of algorithms on to determine different features about songs. Up on the top right, you can see a Spotify code that you can scan to look at the playlist I used for this neural network. For this question, I used the Spotify web API to gather information about 85 songs. And then I classified each song manually as whether I liked it or disliked it, ending out with 50 liked songs and 35 disliked songs. Although I would have liked this data set to be larger, Spotify's web API does limit the amount of songs that you can actually work with at any given time. So for the purposes of this, I only worked with 85 songs, though I would have liked to look at a significantly larger group. I then decided to create a large neural network. And in order to get that kind of small and super simple network, I would trim out layers or reduce the neurons within each layer until I got something that kept the same accuracy while reducing the size greatly. For this question, I had two base models that I wanted to compare it against. The first one is the bland model, as I'm going to call it, which classifies everything as whatever was most popular. In essence, it says, you like all songs, and there's not a song that you don't like, classifying every song as one that I like. Within the testing data set, this ended out with a 37.4% accuracy, and across the entire data set, it had a 58.8% accuracy. The alternative model, which I decided to compare against it as well, was a logistic regression, just base out of the box from the sklearn package in Python. With this, I got a testing accuracy of 42.6% and an accuracy across the data set of 62.9%. And finally is the neural network results that you've been waiting for. On the right, you can see each of these songs. In order to get this data, I worked through the Spotify package within Python. What that allowed me to do is allowed me to work through Spotify's web API within my Python console, take all that information, store it as a CSV, and then read it in as a data frame using pandas. On the right, you have the top 5 songs within that data set, as well as a handful of their characteristics that we used. Again, the neural network structure that I ended up settling upon after tweaking the model repeatedly was a 26 input to 26 ReLU activation function to 1 sigmoid curve neural network. I used that sigmoid curve because that allowed me to do a binary classification on the data fairly easily. With this, I ended up with a testing accuracy of 76.5% and accuracy across the data set being 88.2%. This is pretty remarkable considering that most of the time I still can't determine whether or not I like any given song, and the neural network's able to do it about 88% of the time. I'd like to thank you for listening to my presentation, and I hope you have a wonderful day.